Hello, everyone. Hope you're all doing well. Hi, Abigail. Hey, Colleen. Hope you got to enjoy your Thanksgiving. Maybe not a traditional Thanksgiving, but at least you got to have a break from school. And now we're back, and we have just a little bit left here. Let's take a quick peek at the syllabus. So we are finishing up, or we're starting and finishing up chapter 12, which is alcohols, thiols, ethers, aldehydes, and ketones. You will have your fourth test this Sunday. That will be just over chapter 11 and 12. So it'll be just 2 chapters. Then next week, we're going to move through carbohydrates and amino acids. I'm really going to try and bring some, I'm going to see if I can get carbohydrates in this week a little bit so we're not so crammed next week. And then you have your test 5, and then you have your final, and that's it. So you have 3 exams before the semester's out. These 2 are shorter exams in the sense that they cover less information, right? So just 2 chapters for each of those. So yeah, let's hit it. Let's make it happen. So last week we did alkanes, alkenes, and somebody's saying something. For the final, is there a way to go about studying for it, Janine? As far as the final is concerned, I'd look over your exams. You should be able to look over them. If you don't have access to that, let me know and I will open those up so that you can review them. So that's a really good place. It is just a cumulative final. So really, anything that's been covered on those exams is going to be fair game for the final. You're not going to see something on the final that like we didn't cover in class. Okay, everything should be familiar. So I would go through the objective sheets from each chapter and just sort of, start at the beginning and work your way through. You may find that some of the stuff from the beginning is almost like second nature, right? Like significant figures and stuff like that may start to feel pretty easy. So I would just start at the beginning. And if you're like, I got this, fly through that and then, fill in from there. Ashley, yes. Just stay after class and we'll chat. Okay, so chapter 12 is looking at what we call functional groups. So as if organics couldn't get more complicated, it does, because do our compounds, are they just single chain carbons or double chain carbons? No, there's other things that get stuck to these carbon chains or insert themselves inside a carbon chain. And then we have to change the names even further. So the reason that these functional groups are important is because depending on what, if the carbon chain contains one of these functional groups, it will carry sort of a certain type of property. So alcohols tend to clump together, thiols, ethers, aldehydes, and ketones. So here's an anesthesiologist giving what looks like an epidural, which is if I had one of those with one of my babies, and that was delicious. That was the best $1,700 I ever spent. Just getting that epidural, but it looks like that's what they're doing there. So what that has to do with these things here, different medications have these different accessories to them. So let's look at some examples of each of these. So as far as our functional groups are concerned, and there are more functional groups than the ones that we're going to talk about. Okay, it gets even more complicated, but we're going to look at the main functional groups. So the first one we'll look at is something called an alcohol. So that's where we have our carbon chain and there is specifically an OH sticking off of it. We've already talked about phenol, which is this guy over here, right? That's a benzene ring with an OH sticking off of it. Ashley, that's fine. Yeah. So we've got our benzene ring. right, which has the oscillating double bond, and then we've got this OH sticking off of it. Here's another example of an alcohol. This is methanol, and we'll learn how to name these, but you remember one carbon is meth, and we add methanol. A thiol group, so here's a thiol group. A thiol has an SH sticking off of it. So instead of an OH, it's an SH. The sulfur being the thing that really quantifies it as a thiol. Thiols tend to be kind of stinky because they have sulfur in them. Then we have an ether. This is where we have an oxygen inserted into the main chain. Okay, and we are going to go into more detail on these. But what you can see is we've got a methyl group. It's stuck to an oxygen that's then stuck to another methyl group. The way that I remember ethers is ether or, right? There's one chain here and another chain here. These chains can be quite long or short. One of these chains could be like 6 carbons and another one could be 7 carbons. But somewhere in the middle, there's this oxygen separating them out. So how do we name alcohols? Using our system, we're going to take the E off of our IUPAC name for the carbon chain, and we're going to replace it with OL, okay? So looking at this guy here, this would be methane. If one of these hydrogens instead was an OH group, we would call it methan. We take that E off and we go methanol. Sometimes it's called methyl alcohol, common name. Don't worry about common names, all right? Here's another chain, 2 carbons connected to each other, we would call that ethane. If one of these things had an OH sticking off of it, we would call it ethanol. Ethanol or alcohol. As far as what this looks like, this structure here, so I have carbon bonded to a hydrogen, a hydrogen, a hydrogen. First, let me do the methane and then a hydrogen. This here is this guy right here, okay? The difference between this and this is that one of these groups, whichever one, has, instead of an H, it's got an OH attached to it. This OH. So that's not too bad. Both of these are smaller chains, right? 1 carbon, 2 carbons. So I don't have to specify where the OH is, because in this one, there's only 1 carbon for the OH to be stuck on. In this one, the OH can only be stuck to a terminal carbon, right? An N carbon. What happens when we start to expand beyond 2 carbons? We have to number the chain starting at the end nearest the OH. So remember when we talked about priority and things being more important? OH is more important than any accessories, okay? OH is also going to be more important than like a double or a single bond. So always name and number based off of where the OH is. So looking at this guy here, I've got a chain, find the longest carbon chain. So in this one, 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6, doesn't matter. 6 is going to be the longest. So it's going to be hexane. There is an alcohol, so I'm going to say hexanol. Now I have to tell the reader where the OH is. So I want a number from the OH side, not over here. Okay, so we're going to go with this being 1, 2, 3, 4, 5, and 6. So OH is happening on the second. So it's going to be 2 hexanol. 2 hexanol is going to cover all of this. Then we've got one accessory we have to add. What is that? That's a methyl group and it's on the 5. So 5-methyl-2 hexanol. So there's our hexanol, 2 hexanol, 5-methyl 2-hexanol. Okay. So get in the habit of when you see this OH group, that should indicate to you, oh, that's an alcohol. I want you to name this guy here and name this guy here. Name them both. Just another 30 seconds. Okay, so looking at this one here, this one's actually quite similar to the last one we did. The only difference is that this has a long carbon chain of 1, 2, 3, 4. Either direction will be 5. So 5 will be pentan. Pentan, and we have an alcohol, so it's pentanol. We have to specify where the alcohol is. If this OH is on the first carbon, you do have to say 1 pentanol, okay? So if the OH happened to be over here, sometimes people think, oh, if it's on the first, we can just like not include the 1. That's not the case for this. So we've got 2-pentanol. That covers most of it. We just need to add on this accessory. This is carbon 1, 2, 3, 4. So the methyl's on the 4. So 4-methyl, dash 2-pentanol. This one here, remember, a benzene ring with an OH group on it is phenol. That's the name of that, okay? So you want to know that. Then we just have to add the accessory. So I have a bromine. I'm going to count in a direction that gives that bromine accessory the lowest number. So 1, 2, 3, as opposed to 1, 2, 3, 4, 5. So 1, 2, 3. So 3-bromo. And remember, words that are right next to each other, if there isn't a number in between, you can just smush it together. So 3-bromophenol. Okay, so we've got our pentanol, our phenol. They count them up and add the accessories, 4-methyl 2-pentanol or 3-bromophenol. Any questions on either of those? Okay, I'll give you some more practice after we've added a couple other functional groups. Just FYI, ethanol, which is ethyl alcohol, right? 2 carbons with an OH, has been used since prehistoric times as an intoxicating product. Okay, it's booze. So how do we get this magic ethanol? We take sugars from starches and we ferment them. So we go through this process of fermentation. This sugar will then turn into the ethanol and it'll also give off CO2. You don't need to know a whole lot about this. This is important. So if we have more than one OH group, you have to say that you've got more than one. Whoops, excuse me. So this is, common name is glycerol, but we would call it 1,2,3 propantriol. They use the whole propane, so it's 1, 2, 3, it's 3 carbons. And then they add the TRI, they're the triol, for 3 of these. Okay, if it was only 2, we'd say di. 1, you just get rid of it. So if you come across a situation where there's 2 OH groups, number it in such a way that you go where the OHs will have the lower number. And then if there's 2, it would be di. If there's 3, it would be triol. You probably won't see that a whole bunch, but just have that stored somewhere. Ethylene glycol. So this is, we would say that this is, we would say ethane diol, if we were to use our system name. This is in antifreeze and other things like that. BPA, if you've heard of that, is used to make polycarbonate, which is a clear plastic that they use in manufacturing different water bottles and things like that, also in baby bottles. You may hear things like, it's BPA free. It means that it doesn't contain this here, okay? The reason that you don't want to have BPA in baby bottles or even in your water bottles is that at higher temperatures, you can actually have some of this stuff leach into the water. And it can be somewhat harmful. And also certain soaps can also strip that away too, so. Bunch of different alcohols we find in spices, okay? They start to get a lot more complicated, right? So if we look at, let's say, vanillin, where is our alcohol group? Well, we've got here, it's attached to the benzene. So here's a phenol, but then it has like all these other accessories. You're not going to be naming something this complicated. So don't stress too much about, oh goodness, how would I name something like this? But let's say we didn't have this here, and we had just this, you would have to be able to name that as 2-methylphenol. Here are thiols. So thiols contain that SH group. So they have sulfur. They often have strong disagreeable odors. Sulfur in general is kind of stinky. Skunk's spray contains a lot of these thiols. Also in cheese, onion, garlic, and oysters. I actually kind of happen to like all the smell of those things, but they are quite pungent. They put these thiols in a lot of gases to detect when there's a leak. So when you're in a lab setting and you have natural gas that you're running, and if you smell like a gas leak, you're not actually smelling the natural gas, you're smelling the thiol that they put in there. So here's methanol. If instead of having this OH group, we had an SH, the way that we would name it is we would use the full carbon chain name, methane, and then we would just add thiol to the end of it. Here we've got 2 carbons, this would be ethane, and then we just add thiol to the end of it. If the chain gets longer than 2, you do have to specify where the thiol is. So whereas with the alcohol group, we actually take the E off, we don't take the E off for our thiols, okay? Keep the E on. Why? Because we're trying to confuse you. No, it's just the way it is. So 1, 2, 3, 4, we've got a carbon chain here, 4 carbons, which is going to be butane. There's my thiol group. Thiol's on the second carbon, so 2 butane thiol. Look at that delicious plate of cheese and oyster and onion. Lunch. All right, so we can see the cheese and oysters contains methanethiol. All right, the onion here has 1 propane thiol. So 1, 2, 3, 3 carbons. That's our propane. The thiol here is sitting on the first carbon. 2 propene, 1 thiol. So this is where we have a double bond in combination with the thiol group. Now note that these functional groups that I'm talking about will take precedent over the double bond. So if you notice the double bond gets booted, we're no longer putting the double bond here as this is carbon 1, but we're putting wherever the SH group is carbon 1 because they have a higher priority. Really quickly, you're curious about it. I had this somewhere, but you can find them online. So there'll be sheets there are sheets that have like the actual priority. So like what's the most important functional group? That is really hard to read. See if this is a little better. Okay, so we can see here, you know, our aldehyde, that's like our bromine accessory and things like that. That's lowest on the priority list. Ether is also kind of low. Double bond, or rather single bond, then double bond, then triple bond. Alcohol, when we start looking at ketones and aldehydes, those have higher priorities. All right, so that can be helpful if you're wondering, well, what's more important than what? Oh, come on. Sorry, my computer's freaking out a little bit here. Can you guys see me and hear me? Okay, great. Well, that's all that matters. So let's look at these ethers. So how I like to remember ethers, again, is there's an oxygen and it's set between 2 carbon groups that are either alkyls meaning they're chains, or they're aromatics, meaning they're rings. This tends to have a bent structure, kind of like water. So we would expect to see our oxygen, and then each chain will sort of come off the end like this. I remember this by ether or. So I've got one group and then another group. The way that we're going to name these is that we list each group that's attached to the oxygen in alphabetical order. This thing here is called dimethyl ether because there's a methyl group here and there's a methyl group here. So the ether is covering the oxygen with its bonds. The thing that sits in front of it are kind of like, you can kind of almost think of them as accessories. So dimethyl ether, meaning we have 2 methyl groups. If I was to look at this one here, this guy's a little bit different. We've got our ether group here in the middle. It's attached to a methyl group. And then over here, we've got a 3 carbon chain, which is a propyl group. So we would call this methyl propyl ether. We, again, always put those in alphabetical order. All right, so anesthesia is the loss of sensation and consciousness. General anesthetic is a substance that blocks signals to the brain, so we limit our level of awareness. That's what, like ether. So sometimes this thing is called dimethyl ether, is just called ether. That's what they give you, what they used to give you. So let's go ahead and I want you to write the 3 structures here. We've got 3-pentanol, ethanol, and diethyl ether. I want you to draw the structure, what it would look like. Don't do a full skeletal structure, do a condensed structure at least. Okay, so looking at each of these, when I see this 3-pentanol, I see that OL at the end. I know that there's going to be an alcohol group. So as far as my chain is concerned, pentanol, pentane, that means I'm going to have a bunch of single chained carbons. So C bonded to C, bonded to C, bonded to C. 5 of them, right? 1, 2, 3, 4, 5. All right. On the third carbon, I'm going to have an OH group. Then I've got to fill in my hydrogens. So this has 3. This has 2. This guy actually only has space for 1, right? Because he's got 1, 2, 3. This guy has 2, and this guy has 3. So CH3 attached to a CH2, attached to a CH with an OH, attached to a CH2 to a CH3. Ethanol, that's also an alcohol. Ethane, that means it's 2 carbons. So CH3 bonded to a CH2 that has an OH coming off of it. Could you have put the OH over here instead of over there? Yeah, that would have been fine. Diethyl ether. So ether, I'm just right off the bat going to put an oxygen and I'm going to put 2 bonds. Diethyl means that I have 2 ether groups. So there's a CH2 and a CH3. And then over here, CH2 to a CH3. This is one ether group or ethane group. This is another ethane group or 2 carbons. Okay. Questions on that? So with alcohols, it's not just enough to say, oh, it's an alcohol. We actually want to describe it as a primary, a secondary, or tertiary alcohol. So looking at these alcohols here, we would classify an alcohol as primary, secondary, or tertiary by going to the carbon that's attached to the OH group. Okay, so find, my computer is really struggling here. So find the OH and go to the carbon that it's attached to. And then from there, figure out how many carbons are, or alkyl groups, so they can be longer chains than just a single carbon, are attached to that carbon. So in this situation, this carbon has one carbon group attached to it over here. So 1, 1, that will be primary, right? So it's got one group. Here's my OH. If I go to its carbon buddy and I see how many alkyl groups it has attached, or carbon groups it has attached to it, it has 1, 2. 2 will be called a secondary alcohol. This one here, we go to, from our OH, go to your carbon, see how many carbon groups are attached to it. 1, 2, 3. If there are 3 groups, we know we call it a tertiary alcohol. And that's important for chemical reactions because primary alcohols, secondary alcohols, and tertiary alcohols will all act slightly different from each other. In a way, you can think of it like this. Here, we have a carbon chain. The OH is at the end. So when the carbon chain with the OH at the end, that's going to be a primary. If you have a carbon chain where the OH is in the middle, because see here, this could be carbon 1, 2, and 3. If the OH is somewhere in the middle, that's a secondary. And then if it's in the middle and there's an additional methyl group attached to it, or ethyl or whatever, alkyl group, that's going to be a tertiary. So see, here's the chain. The OH is in the middle of the chain and it has an accessory at that same place. That's also a methyl group that we would call tertiary. Come on. Hold on a second here. If I close some of these things down. Sorry, everyone, my computer is like, everything keeps like moving on it. Can't read anything. Okay. So let's look at these alcohols here. So you want to be able to classify these as primary, secondary, or tertiary. So looking at this first one here, we find our OH group. So let's draw it out. And why don't we name it? While we're at it, let's name it. Okay, so there's 1, 2, 3, 4. There's 4 carbons. So that's going to be butane. And there's an alcohol group. So we're going to call this butanol. And it's on carbon 2. So 2-butanol. So go from the OH, go to that carbon that it's attached to. And then see how many other carbon alkyl groups it has. It's got 1 here. And it's got 1 here. So we would say there are 2 of them. So we would say that this is secondary. Why is that important? Well, you see how it has only 1 H attached to it? That means it only has 1 H to kind of mess around with, because these groups aren't going to break up. And we'll talk about that when we get into chemical reactions in a little bit. This next one, B here, 1, 2, 3. So we have 3, so that's propane. Propanol. The OH is on the first, so it's 1-propanol. Let's take our OH, go to the carbon it's attached to, see how many carbon chain things it has linked to it, or how many carbons touch it. In this case, it only has 1, right? It's got 2 H's, so we would call this a primary. Or if you look at it, this carbon has 2 H's to mess around with. We can pull those H's off and do fun things with them. This one only has 1 H to play around with. What about this last one here? This carbon chain, 1, 2, 3, 4, 5. So that's pentanol. Pentanol. It's on carbon 1, 2, 3. So 3-pentanol. Oh, and there's a methyl group. So it's 3-methyl, 3-pentanol. Go to the OH, find its carbon, see how many like carbons it's connected to. 1 chain here, 2, 3. So 3 alkyl groups. So this carbon doesn't even have any H's. It has no H's to play around with. We would call this a tertiary. So tertiary are for 3. So in general, primary alcohols are more reactive than secondary alcohols, and secondary alcohols are more reactive than tertiary alcohols. Why? Because, sorry, this isn't the secondary. Primary, here's our primary. This is 1, most reactive. Secondary 2, second reactive. Tertiary 3, non-reactive. These hydrogens are what make things reactive, so it can play around with those H's. If you don't have any of those H's on that carbon, you're not going to be able to do anything. Another property of alcohols is whether they're soluble in water or not. So in general, alcohols contain this OH group, which is a polar thing, right? This molecule here is polar. It's got this OH that makes it kind of sticky or grab at the water. So a lot of alcohols will dissolve in water. In general, it has a lot to do with how long the carbon chain is. So the longer the carbon chain is, the less that OH has an effect, right? This is really non-polar, and it's taking up a majority of the molecule. So when you've got something that's mostly non-polar and it has a little bit of a polar quality, it's not going to have quite as a dissolvability quality or solubility quality. What's that cutoff? Well, 1 to 3 carbons are going to be for sure soluble in water. All right, so methanol, ethanol, propanol, those are very soluble in water. The solubility of alcohols will then decrease as you increase the carbon chain. So methanol, ethanol, propanol, all soluble in water. Ethanol, which is alcohol, that like you drink alcohol, usually that's cut with water, right? You don't get a 100 proof alcohol or 200 proof. I don't know how the proofs work, but you don't get 100%. They don't give you 100% alcohol, right? They usually give you something that's less than that. It's diluted with water. When we get into 4, they're slightly soluble. So butanol will sort of dissolve in water. And then we start to get longer chains, 5 and greater, it's insoluble in water. So pentanol, hexanol, these longer things, we're not going to see dissolving in water. Hand sanitizer. Gosh, we're using a lot of that now, aren't we? Hand sanitizers contain ethanol as an active ingredient. You can use it instead of washing your hands. Kills most bacteria and viruses that spread, cold, flu. You can tell that this was written before the coronavirus. There should also be a comma therefore and coronavirus, right? Usually 60% volume, but can be as high as 85%. That starts to get really flammable though. Okay. So are phenols soluble in water? Remember, a phenol is just a benzene ring with an OH off of it. We say that phenols are slightly soluble in water. So if I add water to this, some of it will kind of react with the H2O to produce these H3O molecules, which are antiseptic. They're an acid, but sometimes it will recombine. So we get some solubility, but not 100% solubility. So looking at these, which one would be soluble in water, and explain why. So looking at how long the carbon chain is, B would definitely be soluble in water. Why? Because it's 3 and under carbons. We've only got 2 carbons here. It's short. So the nonpolar side is pretty balanced to the polar side. So the polar side is effective. A would not be soluble in water. Why? Because look at how long this carbon chain is. So much nonpolar properties here that OH just doesn't have such an effect when it has so many carbons kind of counteracting it. All right, so another type of functional group that we have are aldehydes and ketones. So vanilla flavoring, this thing here has vanillin in it, which we talked about. There's an OH group here, but there's also an aldehyde functional group. So both aldehydes and ketones have what's known as a carbonyl group. So they both kind of fall into this carbonyl group thing. And what is a carbonyl group? A carbonyl group is a carbon that is double bonded to an oxygen. This is a very polar connection here because we've got 2 lone pairs of electrons. Also, carbon and oxygen do not share the electrons equally. Oxygen is much greedier, much higher electronegativity, so it pulls the electrons closer to it. So the oxygen on this thing tends to have a relatively negative quality to it. The carbon has a very positive quality to it. So very strong permanent dipole moment happening here. Now, if both aldehydes and ketones have this carbonyl group to them, how do they differ from each other? Well, an aldehyde is at the end of a carbon chain. An aldehyde is attached to a carbon atom that has at least 1 hydrogen to it. So it'll be like this. We've got our chain. This is just a 1 carbon. It's attached to this carbon here. It's double bonded to the oxygen, and then that same carbon has an H to it. Or you can see that the carbonyl group is happening at the end. I remember this one, aldehyde, al at the end. I don't know why that resonates with me, but I've used that since college. So al at the end. So if your carbonyl group is sitting at an N carbon, you're an aldehyde. A ketone is going to be attached to 2 alkyl groups. So whereas in this case, the carbon is at the end of the chain. There's our carbonyl group with the double bond at the end of the chain. Here, our carbonyl group is sitting somewhere in the middle of the chain. All right, that we call a ketone. It kind of looks like, when we're drawing a structure, it kind of looks like a keyhole, right? So ketone, keyhole. You'll have some sort of carbon chain on this side and some sort of carbon chain on this side. Sometimes an aldehyde group is written like this, -CHO. So if you see this somewhere in your formula, that's just denoting that you have an aldehyde group. Let's write this thing out. If I had this, it would be a carbon bonded to a hydrogen, and then there would be an oxygen double bonded. All right, this is the same thing as this. The double bond is just understood. In a ketone, the carbonyl group is bonded to 2 alkyl groups or some sort of aromatic ring. The keto group, C double bonded to O, can sometimes be written as CO. So sometimes you'll see in the middle of a chain, get out of my way, come on. Sometimes you'll see it written like this, okay? So whereas the aldehyde will have the CHO at the end, the ketone will have the CO sitting in the middle. That's not carbon monoxide. All right, it is looking like this. If I was to write it in a skeletal structure, it would look something like this. So we've got our carbon double bonded to the oxygen. Here, the difference being that we've got our carbon double bonded to an oxygen, and then there's a hydrogen, or it's al at the end. Isn't this so much fun? Miss the days of just flip-flopping charges. So naming these things, aldehydes. So as far as the IUPAC goes, when you have an aldehyde, you just take the E off of it and then you add an AL. So al. So if I had a chain that had, let's say, 6 carbons, that would be hexane. I would call it hexanal, AL. Now, there are common names that do know these, okay? If it's 1 carbon, we could call it methanal, or it's called formaldehyde. 2 is acetaldehyde, 3, 4, so on and so on. So know the first 2 at least, especially formaldehyde. That's 1 carbon. If I was to draw out formaldehyde, it would be a carbon double bonded to an oxygen with a hydrogen, and this would also have another hydrogen. So here's our, there we go, our methanal IUPAC. Know how to name it in this way. Okay, and then remember formaldehyde. If it was a 2 carbon chain, you would put it as ethanal, propanal, butanol for 4. Why don't you have to number where the carbonyl group is? Any guesses? Any guesses? No one's going to answer because we're online. But why don't we have to name it? Because an aldehyde, al at the end, it's always at the end. All right, so it's always going to be on carbon 1. So I don't have to specify like over here. I don't have to say that this is 1 butanal. I know that the aldehyde group will be at the 1. Name the longest chain, and then replace the E with an AL. If there are any substitutes, go for that, adding those. Remember that the aldehyde has a higher priority than like bromine or any of those. So looking at this thing here, go ahead and name this thing using the IUPAC. So yeah, go for it. Okay, so the first thing you need to do is make sure that you can identify it as being an aldehyde. That double bond to the oxygen is happening at the end of the chain, al at the end. So count your longest chain with the aldehyde. So I would never do this, 1, 2, 3, right? That's not the longest chain. The longest chain is this 1, 2, 3, 4, 5, 5. So we have pentan. We need to add pentanal, Al will cover that double bond. The only thing we need to do after that is add the accessory. So we have a methyl group right here. We assume that this is carbon 1 because this has high priority. So it would be 2-methyl pentanal. We wouldn't count from this end, right? We always count from the higher priority end. All right, vanilla, cool. Moving on. Okay, naming ketones. So there's a difference with ketones in that you have to say where the ketone is, right? Because if there's a double bond and it's somewhere in the middle of a chain, well, as those chains get longer, it's like, is that double bond, like for this one, for instance, pentanone, 1, 2, 3, 4, 5 carbons, is it going to be on the third carbon here? Or is it on a second carbon? Why wouldn't it be on the first carbon? Because if it's on the first carbon, we wouldn't call it a ketone anymore. We would call it an aldehyde. So just remember, if it's at the end, it's an aldehyde. So with the IUPAC system for ketones, you take the E and you change it to ONE, ketone, own. So there is a common way of naming it. You take each of the attached alkyl groups and you name them in alphabetical order and then say ketone. So like, for instance, looking at this one here, this is butanone, 1, 2, 3, 4. There's 4 carbons, that's the butane. The ONE lets me know that it's a carbon double bonded to an oxygen somewhere in the center. So I don't need to specify, because if I put it on this carbon, that's carbon 2. If I put it on this carbon, that's carbon 2. It won't be on the ends because that would no longer be a ketone, that would be an aldehyde. But another way to name this is to say, here's my carbon, what are the groups? Well, there's a methyl group here and there's an ethyl group here. So you could call it ethyl methyl ketone. I'm not gonna test you on these common name. I'm gonna test you on this here. Okay, so I want you to be able to name that. Looking at this one, 1, 2, 3, 4, 5 methyls, or I'm sorry, 5 carbons. So we're gonna call that pent, and then we add the ONE. And then in this case, we have to say, hey, it's on the 1, 2, the third carbon. Because if this happened to have been here, that would be 2-pentanone. Right? So those are different. What about this thing here? So without the accessory, we would call this cyclohexanone. 1, 2, 3, 4, 5, 6 carbons. They're cyclical, and there's a double bond that's sticking off of it. So cyclohexanone, and then we have an accessory here. So let's do some. So with this one, name the longest carbon chain, replace the E with the ONE, number the carbon chain starting closer to that carbonyl group, and then name and number any substitutes or substituents. So I want you to do this guy right here. Okay, so we'll do some more practice with this too in a little bit, but looking at this one, we find there's a double bond to the oxygen. It's like one of these things is not like the other. So you find the thing that's kind of different or wonky from your traditional single chain, and that's this thing right here. So this is an important functional group. It's not on the end, it's in the middle, so it makes my keyhole. So it's a ketone. 1, 2, 3, 4, 5. So if we have 5, we're pent, right? Pentanone will cover all of this, including that double bond to an oxygen. So the only thing we need to do is add this accessory. I'm not going to count 1 over here. I also need to specify where my ketone is. So I'm going to start from this end, 1, 2, 3, 4, 5. So this is on the second carbon. So it's 2-pentanone because it could technically have been 3-pentanone. Then we add our accessory, 1, 2, 3, 4. So 4-methyl-2-pentanone. As far as aldehydes and ketones in water, so they form hydrogen bonds with water. So we get this oxygen will start to sort of bond with the hydrogen of any surrounding water molecules. So they are very, very soluble when they have 4 or fewer carbons, but not soluble when they have longer hydrocarbon chains, which diminish the polarity. So looking at just a list of some of our aldehydes, 1 to 4-ish, and there's also ketones in here as well. 1 to 4, we're going to be highly soluble. 5 will be sort of soluble. 6 and greater, we lose that solubility again because the non-polar quality of it starts to dominate over that small polar functional group. Important aldehydes and ketones: acetone, that's a solvent that we use in nail polish remover and paint thinner. Methanol, formaldehyde, its common name, is colorless gas with a pungent odor, and they usually put it in solutions to make to preserve different critters and stuff like that. It is also the stuff they pump into bodies. So let's classify these as aldehydes or ketones. So looking at this, so remember aldehyde, al at the end. So here's my carbon chain. In this case, the double bonded oxygen is not in the center, or is not at the end, it's somewhere in the center of the chain. So we would say this is a ketone. This guy right here, where's my double bond? It is to a carbon at the end of the chain, al at the end. So this is an aldehyde. This guy over here, it's got a bunch of accessories, very fun looking, but really we're just trying to decide if it's an aldehyde or a ketone. There's a carbon at the end, double bonded to an oxygen, aldehyde, al at the end. Here we've got a cyclical structure. So this carbon here that's double bonded to the oxygen is bonded to a carbon on this side and a carbon on this side. So we would classify that as a ketone. You can't have an aldehyde in a sort of cyclical structure like this. The aldehyde always has to be at the end of a chain. So name these ketones. Okay, so this top guy here, look at the longest chain, 1, 2, 3, 4, 5, 6. So 6 will be hexane, and we ONE it, hexanone. We have to say where it is on the chain. So this is 1, 2, so it's on the second carbon. So 2-hexanone. Wait, how many? 1, 2, 3, 4, 5, 6. Yes. I don't know why they 1, 2, 3, 4, 5, 6. The notes are a little off a little later on. I'll show you in a sec. So hexanone on the second, 2-hexanone, because we could have been 3-hexanone, right? Or I think, yeah, we could have been 2 or 3-hexanone. No other accessories. This one here, find the longest carbon chain. 1, 2, 3, 4, stop. That's chlorine. Okay. 1, 2, 3, 4 would be butanone, which we're on the 2 butanone. And then we have to give this accessory over here, which is a chloro group. 1, 2, 3, 4. So 4 chloro, 2 butanone. Hexanone, butanone. 2 hexanone, 2 butanone. I don't know why it changes to 2 pentanone here. That's where it's incorrect. Okay, it's still hexanone. So we're going to go with 2 hexanone for that. So if you see that in your slides, hexanone, that's what's happening. The butanone is encompassing this whole thing. We add the accessory after the fact. Questions on that? On naming? Okay, I'm going to keep rolling through lecture, and then what I want you guys to do is go through your notes and maybe even start working on the lab. And then next time we can ask questions about naming and stuff. I want you to practice a little bit before I go over too many examples. So I want to be, we get kind of crunched at the end of the semester. So I just want to be really poignant about what we're going over. So let's continue on. So reactions of alcohols, thiols, aldehydes, and ketones. We're not going to be worrying at all about reactions of thiols. So in general, I don't do a whole lot of testing on thiols. We tend to be more on the alcohols, aldehydes, and ketones. Okay. So the first type of reaction that we're going to talk about is known as dehydration of an alcohol. So alcohol undergoes dehydration when we heat it and we add an acid catalyst. So we can see in this equation here, this has an alcohol on the left-hand side. There's an arrow, and above the arrow, it says H plus and heat. What's the H plus? Remember, H plus is an acid, and then heat. So here's my alcohol. Specifically, this is 2 carbons, so ethanol. You see how 1 carbon has the OH, it's the alcohol component, and then the carbon it's attached next to it has a hydrogen. Well, what is occurring when we undergo dehydration is this OH and this H bond together to form water. If that happens, and these guys, these 2 carbons lose this buddy here, well, they're short one of their 4 bonds. So what they're going to do is that's going to sort of close up and it will double bond, or we'll get an alkene. So alcohols will dehydrate, or they'll lose an OH and an H to form an alkene. Doesn't really matter how long this chain is. We will get that double bond. So let's do, I'm going to have you do a made up one. Okay, so I want you to draw an equation for the dehydration of 2-pentanol. So draw the equation for the dehydration of 2-pentanol. So that thing that we just looked at, that was for ethanol, I want you to do it for 2-pentanol. Okay, so for 2-pentanol, this is an alcohol. Alcohols, whenever they undergo dehydration, are always going to form an alkene or something with a double bond. So if I draw this thing out, it would be carbon bonded to a CH, and this thing has an OH bonded to a carbon, and I'm going to actually put its H there and its H there just for its adjacent one here. And then we've got CH2, 1, 2, 3, 4, 5, something like that. If this thing undergoes dehydration, it means that I need to add acid and heat, not water. And what ends up happening is the spot where the alcohol is going to, that OH is going to bond with an adjacent hydrogen from a neighboring carbon. Okay, so these two things are going to come together, and that's going to form H2O. Okay, that's where the H2O or the dehydration is coming from. Then that leaves these guys down a buddy. So they need to fold in or bond with each other. So what will end up happening then is we've got this CH3 bonded to a carbon with a hydrogen that is now going to be double bonded to its guy. And I'm going to put this hydrogen back in here. CH bonded to a CH2, bonded to a CH3. That's how dehydration goes. Could I do a chain that has 9 carbons? Totally. What's going to happen, the magic step of the dehydration process is this right here. It's where your OH or your alcohol combines with an adjacent H to give you water, and then it folds in to make a double bond. We've got just a couple minutes. I'm going to talk about oxidation reduction really quickly. My pen does not want to work for me. All right. So in organic chemistry, when I'm talking about oxidation and reduction, we've talked about oxidation and reduction in the inorganic section, right? Where oil rig, oxidation is loss of electrons, reduction is gain in electrons. Well, in organic chemistry in general, oxidation reactions increase the number of carbon-oxygen bonds. Okay, so anytime you have a carbon and it bonds to an oxygen, or you have a carbon and it can double bond to an oxygen, that is oxidation. Another way to think about this is we lose hydrogens. Hydrogens go away. Hold on, it's like Lauren, I thought for the pentanol, the OH would start at the end. That's fine. If it didn't specify which hydrogen, that would have been fine. That would have been fine. Reduction reactions reduce the number of bonds between carbons and oxygens, or reduction is when you put hydrogen back in. So if I have an alkane here, this thing has no bonds to oxygen, right? There's no oxygen in this single bonded structure. If I oxidize it, I'm going to add oxygen. The first step in oxidation is to put an OH on one of those carbons. So alkanes will always oxidize to primary alcohols, right? Or we have an OH connected to the end of our chain here. After that, primary alcohols, if I want to oxidize this thing, what do I need to do? I either need to increase the number of carbon-oxygen bonds, or I need to decrease my hydrogen, or both. So the alcohol will then oxidize to what's known as an aldehyde, right? So that carbon that was bonded to the OH, the carbon made another bond with the oxygen. Because it made another bond with the oxygen, the H had to go away. So it lost the H. This carbon here, because it was going to now double bond with the oxygen, it lost one of its open 4 slots. So it also had to ditch one of its hydrogens. And so this went away and one of these hydrogens went away. And now we have an aldehyde group. We can oxidize this even further into what's known as a carboxylic acid. So we take our carbon here. It's double bonded to this oxygen. I can't put another bond here, but I could stick an oxygen here and make that like an alcohol there. So now we have carbon bonded to 1, 2, 3 oxygens, or not bonded to 3 oxygens, but there's 3 bonds associated with bonds to oxygen. So alkanes to alcohols, alcohols to aldehydes, aldehydes to this carboxylic acid group. When we're oxidizing, we're increasing bonds to oxygen. If we go in the opposite direction and we reduce it, we're going to decrease. So a carboxylic acid can reduce to an aldehyde, and an aldehyde would reduce to an alcohol, and alcohol would reduce to an alkane. We will definitely talk more about this. We will go through these different oxidations. So don't stress too much about this yet. But the naming portion of it, I want you guys to have the namings down. So you might want to start working on those labs so you can name alcohols, ketones, and aldehydes really, really quickly. Okay. We'll stop there. If you have any questions, let me know. Ashley, send me an email directly about meeting up, talk about that lab. If anybody else wants to stay around and chat, we can do that. Otherwise, have a good rest of your day. And I will see you all on Wednesday.